Welcome all. Now we are going to discuss some examples in the section 10.7. First we will see an example for the closed graph theorem and the open mapping theorem does not hold if x or y are not Banach spaces. Okay. Consider x equal to y equal to c naught naught with norm infinity. We know that here x and y are not Banach spaces, and consider the map f from x to y defined by f of x of j is equal to j into x of j for j equal to 1 to 3 etc. That is, for x equal to x of 1, x of 2 etc. Capital F of x is defined by x of 1, 2 into x of 2, 3 into x of 3 etc. Okay, then we can clearly see that f is linear by checking f of x1 plus x2 of j is equal to f of x1 of j plus f of x2 of j, and f of cx1 of j is equal to c into f of x1 of j. Okay, so here f is a linear map. Now f is a closed map because for xn converges to x in x and f of xn converges to y in y, we get xn of j converges to x of j for j equal to 1 to 3 etc. Hence f of xn converges to y in y implies f of xn of j converges to y of j, but f of xn of j is j into xn of j, means j into xn of j converges to y of j, but actually j into xn of j converges to j into x of j. Okay, so we have j into x of j is equal to y of j for every j equal to 1 to 3 etc. This means that f of x of j is equal to y of j for every j, means f of x is equal to y. That is, if xn converges to x and f of xn converges to y, then y is equal to f of x, means f is a closed map. So we have now f is a closed linear map from x to y. But here f is not continuous, because if we let xn is equal to the sequence 0 0 etc 1 0 0 etc, the 1 occurs in the nth place, then norm infinity of xn is equal to the supremum value of the entries, that is equal to 1 clearly for every n, and f of xn by definition, that is equal to 0 0 etc n 0 0 etc. That means the n occurs in the nth place and all other entries are 0. This means that norm infinity of f of xn is clearly equal to n, which tends to infinity as n tends to infinity. This means that the function capital F is not bounded, and so it is not continuous. Okay, so we have found a closed linear map f which is not continuous by the closed graph theorem. If the space x and y are Banach spaces, then every closed linear map is continuous. So here closed graph theorem fails because here x and y are not Banach spaces. Okay, now consider the map, the inverse map of the function above, that is f inverse from y to x, defined by f inverse of y of j is equal to y of j by j for every y element of y and j equal to 1 to 3 etc. Here also x is equal to y is equal to c naught naught with the norm infinity. Okay, so this function f inverse is just the inverse function of the function capital F we have met before. So for y equal to, that means this function f inverse is defined actually by for y equal to y of 1, y of 2 etc. f inverse of y is equal to y of 1, y of 2 by 2, y of 3 by 3 etc. Okay, clearly as we seen before, f inverse is linear, and here f inverse is surjective also, because for x equal to x of 1, x of 2 etc. element of capital X, we can choose y equal to x of 1 into x of 1 comma 2 into x of 2 etc. j into x of j element of y. Then we can clearly see that f inverse of y is equal to x, means f inverse is surjective. Also F inverse is closed because F inverse is continuous. That is, if we check norm infinity of F inverse of y, which is equal to, by the definition, supremum of all mod F inverse of y of j, where j equal to 1 to 3 etc., that is equal to supremum of all mod y of j by j for j equal to 1 to 3 etc., which is less than or equal to supremum of all mod y of j equal to 1 to 3 etc. Okay, which is actually norm infinity of y. So this means that norm infinity of F inverse of y is less than or equal to 1 into norm infinity of y, means that F inverse is continuous by theorem 6.2. Since every continuous map is closed, here F inverse is a closed map. Okay, so we have F inverse is a closed linear surjective map, but F inverse is not open because F inverse is because F is not continuous. Okay, so because F inverse is open means inverse image of open sets must be open. Okay, but F is not continuous here, so inverse image of open sets are not open here. That means F inverse of open sets is not open. This means F inverse is not an open map. Okay, so we have seen a closed linear surjective map which is not open, but open mapping theorem says that if X and Y are Banach spaces, then every closed linear surjective map is open and so continuous. But here open mapping theorem fails because here X and Y are C0 which is clearly not a Banach space. Okay, now another example for closed graph theorem fails. That means example for a closed linear map which is not continuous. Here we are choosing capital X equal to C dash of AB and capital Y equal to C of AB, both with norm infinity. Clearly Y is a Banach space and X is not a Banach space. Okay, because X is a proper dense subspace of Y actually, so that cannot be Banach. Okay, now define the map F from X to Y by F of X is equal to X dash. Clearly F is linear because F of Cx plus Y is equal to C into F of X plus F of Y. So F is linear. Now we will see that F is closed because if we choose Xn, a sequence converging to X in capital X, and F of Xn converges to Y in capital Y in norm infinity, this means that Xn converges to X uniformly in capital X, and F of Xn, which is Xn dash, converges to Y uniformly in capital Y, because convergence in subnorm is actually the uniform convergence. Okay, so since each Xn is differentiable, the convergence is uniform, and so the limit point X is differentiable, and limit Xn dash is equal to X dash. That is, X dash is equal to limit Xn dash is equal to Y. That means Y is equal to X dash. Y is equal to X dash, which is actually F of X. So if we choose Xn converges to X and F of Xn converges to Y in Y, then Y is equal to F of X. Means that capital F is a closed map. Okay, so now we have capital F is a closed linear map. But here F is not continuous, because if we let Xn of t equal to the functions t minus a by b minus a raised to n for t element of closed interval ab and n equal to 1 to 3 etc., clearly norm infinity of Xn is the supremum value, that is actually equal to 1 for every n. But F of Xn is the derivative of Xn, that is equal to n into t minus a by b minus a raised to n minus 1 into 1 by b minus a, and norm infinity of F of Xn is equal to n by b minus a, which is tends to infinity as n tends to infinity clearly. This means that F is not bounded here, and so F is not continuous. So here we have seen a closed linear map which is not continuous, means the closed graph theorem fails here, because here X is not a Banach space. X is not a Banach space, but Y is a Banach space. Okay, the closed graph theorem agrees only with X and Y are Banach spaces, but here one of the spaces X is not a Banach space, and so closed graph theorem fails here. Okay, now we will see another example for a closed surjective linear map which is not open. Okay, that means another example for open mapping theorem fails. Here also we choose capital X equal to C dash of AB with norm X is equal to norm infinity of X plus norm infinity of X dash, and capital Y equal to C dash of AB with the subnorm. Okay, the same spaces with different norms. Clearly X is a Banach space, but Y is not a Banach space. Okay, define capital F from X to Y by f of X is equal to X. Then clearly F is linear, and F is closed also because F is continuous. That is, norm infinity of f of X is equal to norm infinity of X, which is clearly less than or equal to norm infinity of X plus some other quantity, norm infinity of X dash. That is nothing but equal to norm X. So this means that norm infinity of f of X is less than or equal to norm X, means F is continuous and hence it is closed. So we have a closed linear map F, which is surjective also, because the map is clearly f of X is equal to X is surjective also, but here F is not open because F inverse is not bounded. Okay, because F inverse is defined from capital Y to X is not continuous, because norm of F inverse of Y is equal to norm Y, which is norm infinity of Y plus norm infinity of Y dash, means F inverse is not bounded, because if we choose Yn as the sequence, Yn of t is equal to t minus a by b minus a raised to n for t element of closed interval ab and n equal to 1 to 3 etc. We can say that norm infinity of Yn is equal to 1 and norm infinity of Yn dash is equal to n by b minus a, and so norm infinity and so norm of F inverse of Yn is equal to 1 plus n by b minus a tends to infinity as n tends to infinity, means F inverse is not bounded, and so F inverse is not continuous, and so F is not open. Okay, so we have seen that a closed surjective linear map from X to Y is not open, means open mapping theorem fails here, because here both X and Y are not Banach spaces, only X is Banach here, but Y is not Banach. That's so here open mapping theorem fails. Now we will see another example for a closed projection which is not continuous. Okay, we choose the space capital X equal to C dot naught with norm infinity. Clearly we know capital X is not Banach. Now consider the map P from X to X defined by P of X of 2j minus 1 is equal to X of 2j minus 1 plus j into X of 2j, and P of X of 2j is equal to 0 for X element of X and j equal to 1 to 3 etc. That is, for X equal to X of 1, X of 2, X of 3 element of capital X, we have defined P of X is equal to first coordinate is X of 1 plus X of 2, and the second one is 0, third one is X of 3 plus 2 into X of 4, and the fourth one is 0 etc. Okay, that is, in the even places we have 0, and in the odd places we have X of j X of j 2j minus 1 plus j into X of 2j. Okay, then clearly we can see that P is linear by checking P of Cx plus y is equal to C into P of X plus P of y, and also P is a projection because P square of X is equal to nothing but P of X. Okay, so now we have P is a linear map and is a projection. Also we have R of P is equal to set of all X element of X where X of 2j is equal to 0 for every j, and Z of P is equal to set of all X element of X with X of 2j minus 1 plus j into X of 2j is equal to 0 for every j. Clearly these both R of P and Z of P are closed subspaces of capital X, because if we choose R of P and a sequence xn in R of P with xn converges to X, Then by this we can see that xn of 2j converges to x of 2j for every j, but xn element of R of p means xn of 2j is equal to 0 for every j, and so the 0 sequence converges to 0 clearly, and we get x of 2j is equal to 0 for every j. This means that x is an element of R of p. Okay, that means if we choose a sequence xn in R of p with xn converges to x, then that x should be in R of p. This means that R of p is closed. Similarly, we can say that Z of p is closed. Okay, then by theorem 10.3 we can say that P is a closed map because R of p and Z of p are closed, and so P is a closed map. But here P is not continuous because if we let xn be the sequence 1 1 1 1 etc. 1 0 0 etc., that is 1 occurs in the first 2 n entries, then norm infinity of xn is equal to clearly 1 for every n, and p of xn is equal to by the definition which is equal to 2 0 3 0 etc. n plus 1 0 0 0 etc. Okay, from this we can say that norm infinity of p of xn is equal to n plus 1, which is clearly converges to infinity as n tends to infinity. So this means that p is not bounded and hence p is not continuous. Okay, so we have a projection, a closed projection which is not continuous. Since this happened because x is not Banach here. Okay, thank you.